Hi, let's talk about compound interest. That's what section 3.2 is all about. So in this section, what we're going to do is we're going to focus on investments in which interest is compounded. So in other words, if the interest is reinvested, okay, that's what it means. Having interest earn interest is called compounding the interest. It's called compounding the interest. Another definition, the length of time between the deposits of interest back into the account is called the compounding period. That's called the compounding period. Okay, that's a D. Okay, now let's talk about compound interest, or at least identify what the formula is. This is the compound interest future value formula. The future value of an investment of P dollars earning compound interest at a rate of I per compounding period for N periods is given by F equals P times the quantity 1 plus I raised to the nth power. Okay, so this is compound interest whenever you're looking for the future value. Okay, now you should star that. You have to remember it. Okay, now let's talk about compound interest. That's the future value formula based on years. And this one should be familiar to you because we used this in our previous chapter. The future value of an investment of P dollars earning interest at an annual rate of R compounded M times per year for T years is given by F equals P times the quantity 1 plus R over M raised to the MT. Okay? And this formula you've seen, but notice that you're seeing it again in terms of the future value formula based on years, so you should start remember it. Okay? A given amount of money received now will usually be worth a different amount to us than the same amount received sometime in the future. This is called the time value of money. That's called the time value of money. Okay, so now let's look at an example. Let's see how to use the things that we've learned. Okay, example 1. It says you invest $10,000 in rapid growth funds, which appreciate by 2% per year with yields reinvested quarterly. By how much will your investment have grown after 5 years? So here, the fact that we're trying to find out how much our investment will have grown after 5 years, that means we're looking for a future value. We're looking for F. Okay. Now, well, what formula do we use? Okay, do we use the one from page 1 or do we use this one here? Well, we're given our rate of I. Okay, our rate I, we can figure out. We're given out our actual investment, which was P, and we can figure out our N, which is the number of periods. Okay, so let's use the formula from page 1 that says F is equal to P times the quantity 1 plus I raised to the nth power. Okay, now P, let's write out the information that we know. P is equal to 10,000 because it says we invest $10,000. And then it says that this appreciates by 2% per year with yields reinvested quarterly. So we know that I is going to be 0.02, that's coming from your 2%, divided 4 because we are reinvesting quarterly, which is going to give us 0.05. N is equal to 4 times 5, right? Because we're investing quarterly for 5 years. So that's going to be equal to 20, which means that F is equal to 10,000 times the quantity 1 plus 0.005 raised to the 20th, and that's equal to 10,000 times the quantity 1.005 raised to the 20th, and you enter that into your calculators, and that gives you approximately $11,048.96. Okay, but what was our original question? It said, by how much will your investment have grown after 5 years? So let's make sure we answer that question. So that means we have to take this amount, subtract 10,000, and that result will be our answer. So the deposit will have grown by, let's give ourselves a little bit more room, and then we moved everything. So let's fix that. By, we take the $11,048.96, subtract 10,000 from that, and that gives us $1,048.96. That's how much it will have grown. So now let's talk about the present value for compound interest. Let's talk about the present value for compound interest, okay? So the present value of an investment with future value F is given by P equals F divided by the quantity 1 plus I raised to the N, or F times the quantity 1 plus I raised to the negative N. Okay, so recall that 1 over x to the n is the same thing as x to the negative n. That's how we get from this step to this step. Okay, or we can use the formula P is equal to F divided by the quantity 1 plus R over M raised to the MT. Now notice that these really aren't new formulas. These are the formulas from pages 1 and 2, but it's just that we solved them for P. Okay, so I is your interest rate per period, N is the number of compounding periods, R is your annual interest rate compounded M times per year, and T is your time in years. Okay, a fact that has a couple of new terms: a bond pays interest until it reaches maturity, at which point it pays you back an amount called its maturity value. Its maturity value, or some people call it the par value. Okay, so let's look at an example together and include this table in your notes. Okay, so include this table here in your notes. If you bought Bank of America bonds with a maturity value of $5,000, how much did you originally pay? Okay, so here we're being asked for our P. And then we're looking in at the Bank of America bonds. So we know that N, the number of compounding periods, would be 10. And we know that our interest rate per period would be 3.42%. Okay, so we're looking to find P. So let's use this formula here. Okay, so P is equal to F divided by the quantity 1 plus I raised to the nth power. Well, we know that our future value is $5,000. We're going to divide that by 1 plus. Notice that we have 3.42%, which is equivalent to 0.0342. So we're going to have plus the quantity 0.0342. All of that raised to the 10th power because of this 10 here. Okay? It's not a highlighter. So this 10 corresponds to this 10. Okay? So we then have this is 5,000 divided by the quantity 1.0342 because we added what was inside parentheses, raised to the 10th power. Okay? You enter that into your calculators and you get this is approximately $3,572.11. So I hope you pause the video to try that. Now remember, if you're entering this into your calculators, you want to put 5,000 divided by this quantity raised to the 10th. Okay? All right. Let's move on. Let's look at another example. Example 3. Let's talk about inflation. Okay? Inflation has been running 1% every 6 months. A car now costs $30,000. How much would it have cost 5 years ago? Okay, so again, we're wanting to find P. P is equal to F divided by the quantity 1 plus I raised to the nth power. Here we know that F is equal to $30,000 because that says what a car now costs. Now costs $30,000. And then we have that I is 1%. So I is equal to 0.01. That's coming from the 1% here. And then N is the number of compounding periods. So we know that it was compounded every 6 months, which means that's twice a year for 5 years. So N would be equal to 5 times 2, which is equal to 10. So again, we have 6 every 6 months, which means it's twice a year times 5 years. Okay, so this means that P is equal to F divided by this. So now we substitute our values. So we have 30,000 divided by the quantity 1 plus 0.01 raised to the 10th power. That's equal to 30,000 divided by the quantity 1.01 raised to the 10th. And whenever you enter that into your calculators, what do you get? Pause the video and try it. You get, it's approximately 27,000, that's a 2, $27,158.61. Okay? Now let's talk about one last concept in this section and then we'll do an example. And that will be section 3.2. Let's talk about nominal and effective interest rate. The nominal annual interest rate of an investment paying compound interest is the original or your quoted annual rate. The effective annual interest rate is the actual percentage interest paid by the investment over 1 year, and it equals the annual rate that would result in the same interest if interest were compounded annually. Okay, now the effective interest rate, which we'll write as R sub EFF, of an investment paying a nominal interest rate of R sub NOM, that's for the nominal interest rate, compounded M times per year, is given by the effective interest rate equals the quantity 1 plus R subnom, or your nominal interest rate, divided by M, that quantity raised to the nth power minus 1. Okay? So you should remember this formula because you'll be using it. Okay? So let's look at an example here. You are offered 3 investments. The first promises to earn 15% compounded annually. The second will earn 14.5% compounded quarterly. And the third will earn 14% compounded monthly. Which is the best investment? Okay, so we need to remember here that R sub F, EFF, is equal to the quantity 1 plus your nominal interest rate over M raised to that quantity raised to the M minus 1. Okay, and also note here that you want to, whenever it asks us which is the best investment, that means we want to compare the effective yields, of the 3 investments. Okay, and whichever effective yield is the greatest, that will be the best investment. Okay, so let's take a look. Okay, your first investment. So for the first investment, it says the first promises to earn 15% compounded annually. So if it's compounded annually, that means our M is 1. So this means M is equal to 1. And it says it earns 15% annually. So that means our nominal interest rate is equal to 0.15 or 0.15. That's comes from the 15%. Okay. Now, using this formula, that gives us that, notice here that M is 1 here, M is 1. So you would have your effective interest rate is equal to the quantity 1 plus 0.15 over 1, all of that raised to the 1 minus 1. Okay, well, that's equal to 1. You can drop the parentheses, they're not needed. So 1 plus 0.15 minus 1. Your 1's cancel, and you're left with 0.15, which means you have 15%. Okay? It has an effective yield of 15%. Okay, now what about the second investment? I encourage you to pause your video and write down the effective yields for the second investment and for your third investment. Okay? And then come back and compare what you got. Okay? So your second investment means we're now zooming in on what happened here. The second will earn 14.5% compounded quarterly. So that means here that our nominal interest rate is equal to 0.145 because that's equivalent to the 14.5% interest rate. And then our M, because it says is compounded quarterly, that means M is equal to 4. That means M is equal to 4. So now we substitute this into our formula over here, and we get our effective interest rate is equal to the quantity 1 plus 0.145 divided by 4, that quantity raised to the fourth power, all of that minus 1. Okay, now because we're raising this quantity to the fourth, we can no longer do like we did in the first part and just drop the parentheses. You actually have to figure out what this is. So if you're entering this into your calculators, you enter this quantity in parentheses, raise that entire thing to the fourth, and after you get your answer, subtract 1. Okay, whenever you do that, you'll get that that's approximately 0.1531, or remember you're wanting that in terms of percent. That means you have 15.31%. Now remember, it's because you're moving this to the right twice or you're multiplying by 100. Okay, now let's see what happens with our third investment. So our third investment will earn 14% compounded monthly. So our third investment we have our nominal interest rate. It says 14% compounded monthly. So our nominal interest rate is equal to 0.14. And M, since it's compounded monthly, that's equal to 12. So our effective interest rate is equal to the quantity 1 plus 0.14 divided by 12, this entire quantity raised to the 12th power, minus 1. Whenever you enter that into your calculators, you get that that's approximately 0.1493, or in other words, 14.93%. Now, if we're comparing the effective yields, the first investment was a 15% effective yield. Here, we had for the second investment a 15.31% effective yield. And here, for the third investment, we had a 14.93% effective yield. This is the best, right? So that means that the second investment was the best. Okay, so we can conclude the best investment is the second, which was the 14.5% compounded quarterly. Okay, so that concludes section 3.2.